Okay, awesome. Well, it is my honor to introduce today's seminar speaker. Um, this is Tina Liu. She is an assistant professor in the Department of Geography at the University of British Columbia. Tina was a NOAA Climate and Global Change postdoctoral fellow at the University of California, Irvine. And so we were in the same lab together when I was a graduate student. Tina was a postdoc, same department as Kyle, who I heard in the room. Um, she completed her PhD in Earth and Planetary Sciences at Harvard University, uh, and a BA in Environmental Science at Columbia University. Tina is an interdisciplinary environmental scientist who uses a combination of remote sensing, GIS, data science, and atmospheric modeling to understand modern human-fire relationships, the role of fire in the Earth system, and the impacts of extreme events on planetary health. Broadly, her research lies at the intersection of atmospheric science, geography, and public health, with a special focus on India, Equatorial Asia, and North America. Welcome, Tina.
Okay. Thanks, Nicole, for that really great welcome. And also thanks everyone for the invitation to present here today. I'm really excited to talk about some of my recent research, particularly during my postdoc at UCI. During my PhD, I mostly focused on agricultural fires in India and also forest fires in Equatorial Asia. But having grown up in California, wildfires has become a really kind of pressing issue and has become very destructive as well. So I was ready to kind of transition my research back to wildfires in North America. So today I'm going to be talking about sort of building data-driven frameworks for modeling large wildfire growth, um, both mapping fire progression and talking a little bit about understanding drivers of fire spread as well. And so first I want to acknowledge my collaborators at UC Irvine as well as NASA. And today I'll be particularly showing work done by Andrea Delgado, who is a postbac at UC Irvine working with Jim and I on several projects, and also Yang Chen's work on developing fire tracking algorithms using Veer's active fires. Okay, so the outline for today's talk is going to be firstly on data advances and challenges, both in terms of the remote sensing of fire progression and kind of looking and mapping its characteristics, and also looking at agency reports of suppression resources and personnel. And this is also building on a lot of the work already done at Earth Lab as well. So I'm really grateful for the work done by all of you. And secondly, I'll be talking about how we're applying some of these derived data sets to applications in wildfire modeling, particularly in constructing data tables and data cubes for modeling, for example, wildfire growth, and also looking at key parameters for modeling fire growth using these agency reports. And finally, I'll talk a little bit about smoke modeling and land management and a recent paper that was done by one of my mentees, undergraduate at Harvard, kind of developing a framework for evaluating smoke burden from wildfires in California and tracking the or evaluating the effectiveness of pre-fire land management strategies. And so I just wanted to start with sort of an introduction on wildfire feedbacks. So as we all know, there's been an emergence of large destructive wildfires both in Western US and Canada in recent years. For example, in 2020 and 2021, 2023. Um, and so we have several factors that's been contributing to these large destructive wildfires, namely climate change, but also the legacy of fire suppression policies that has led to a buildup of fuels. And finally, the growing human populations in the wildland urban interface that has led to increased ignitions in these areas as well. And these wildfires have really destructive impacts for human health and air quality. And part of my other work is on kind of air quality modeling and atmospheric modeling. So my work is kind of a combination of both remote sensing and GIS and also atmospheric modeling. And so the main questions I wanted to talk about today is basically how do we effectively model wildfires and their impacts? And to do this, we need to improve our mapping capability of fires, but also quantify various drivers of fire growth. So looking at, for example, weather and climate or land cover and fuel, topography and suppression. And secondly, we need to ensure that we have a good understanding of all of these data sets, the strengths and also drawbacks of various types of data sets, for example, from remote sensing and satellite data or from agency reports. And so first, let me talk a little bit about remote sensing of fires and also how we map fire progression. So as we know, we have different types of satellites. The most common one type that has been used in fire progression mapping is low Earth orbit satellites, namely Terra and Aqua or SMPP, so MODIS and VIIRS active fire detections. So the frequency of these observations are generally twice per day. And this is in contrast to geostationary observations from the GOES satellites over North and South America. So we have both the GOES East and GOES West satellites, and they observe this region very frequently. So in CONUS, this is about every 5 minutes, and over the full disk region, this is 10 to 15 minutes. And active fires are detected as these thermal anomalies or hotspots relative to cooler background pixels. And so this is kind of just the temporal range of some of these data sets that some of these you might be very familiar with, namely Landsat, which has a really long record, but low temporal frequency, and then going to MODIS and VIIRS, which is daily to twice daily. And these are lower in spatial resolution. So Landsat is the highest in spatial resolution of 30 meters, and then going to MODIS and VIIRS from 375 meters to 1 kilometer. And then we also have GOES. I only put GOES R here, but GOES also has a pretty long record. So now we have GOES R, so in particular, GOES East and GOES West, which has a lower spatial resolution of 2 kilometers at the equator, but very high temporal frequency of 5 to 15 minutes. And what's also nice about some of these data sets is that they're available on Google Earth Engine, which I use a lot to kind of develop my fire tracking algorithm. And I'll talk about this a little bit later. And so let me talk a little bit about some of the work that has been done in Jim's lab, in particular by Yang Chen, who has developed the FES algorithm, which uses VIIRS active fire detections to map 12-hourly fire perimeters. So this is showing the VIIRS active fire detections in the red dots here. And the lines here, or contours on this map, represent the 12-hourly perimeters of the Caldor fire. And you can also see how the fire is progressing both with time and space. So the colors represent kind of the timing of that perimeter relative to ignition. And from these satellite observations, we can also derive other characteristics like active fire lines or fire spread rates and looking at fire intensity along the active fire line as well. But efforts to map fire progression has been so far limited to mostly using MODIS and VIIRS, which lack high temporal resolution. So they've been mostly limited to 12-hour or daily intervals. And I also wanted to just go deeper into how this algorithm works. So first, this is an example for this should be actually Bobcat Fire of 2020, but so we start with a set of active fire points, and this is just showing the VIIRS 375-meter active fire detections for the Bobcat fire. And what the FES algorithm does is it creates triangles between all of these points using the Delaunay triangulation. And so you create this 10 or triangulated irregular network. And so you create this kind of network of triangles that connect all of these points together. And what you do in the next kind of step of this process is to create an alpha shape, which basically filtering all of these polygons by some threshold of the longest distance of these triangles, and then dissolving all of these triangles that meet this criteria. And you get this final perimeter in red here, which is going from this set of polygons to one singular polygon at the end. So this is a vector to vector-based analysis. And NASA also has this algorithm in real time on the firm's website as well. So you can also check it out under the experimental products data sets. And we also have a website that lists some of the FED's data sets, including the original algorithm and also other kind of modifications of this algorithm for various regions, including boreal Arctic fires as well. And another type of fire tracking that I've seen, and I was really interested in this because this was done in Earth Engine. And Earth Engine, if you don't know, is a cloud-based platform for geospatial analysis. So it's very similar to ArcGIS or QGIS, but they have a lot of these geospatial and remote sensing data sets already loaded on the cloud there. So it's really easy to work with these data sets, particularly big geospatial data sets. And what's nice is they've loaded the newer GOES data sets onto this platform, including GOES East and GOES West under the GOES R series. So they have these high kind of temporal frequency active fire detections from 2019 or so. And so they also published this article. I think this was back in 2019 or 2020. And what Google wanted to do is to make this near real-time tracking in Google Maps. So if you go in Google Maps today, you can actually see this wildfire layer. And this is showing a screenshot that I took last year. And this was the near real-time perimeter of the Jasper fire in Canada back in July. And so the question I wanted to tackle during my postdoc was how we can leverage geostationary satellite data with high temporal frequency to improve fire tracking and also representation of the fire diurnal cycle. Because for a lot of these large wildfires, they tend to spread very rapidly. So with the 12-hour or daily interval, we can't see at much higher temporal frequency some of the detail of how the fires are spreading. And so this is a pictorial depiction of kind of the updated version of that algorithm I came up with this is tailored to fires in California. So I was looking at fires above 50,000 acres from 2019 to 2021. And this is showing an example for the final fire perimeter for the Creek Fire in 2020. So we start with the fire pixels for goes east and goes west. And what you'll notice is that the pixels have different spatial resolutions and also different orientations because of their locations relative to California. So goes east has lower spatial resolution than goes west. So for this fire, the pixel size is about 3.2 kilometers for goes east and 2.5 kilometers for it goes west. And the colors here represent this fire detection confidence that was first introduced in that blog article by Google. And basically, you transform the quality of each pixel into this continuous value between 0 to 1, where 1 is you're highly confident that that pixel was burned, and 0 means that no pixels were burned at that location. And you'll also notice that generally pixels are more highly confident in terms of the detection in the interior of the fire, and around the edges, you have more low confidence pixels. And what you can also do is to overlap these two satellite observations in order to create a downscale resolution. So using these two satellites, we can get a downscale resolution of about 1.7 kilometers using the intersection of these pixels. And so in the next step, what we also had to do is to apply a terrain correction because for fires that are at really high elevations, the pixels are actually displaced from their actual location on the ground. So we had to use an elevation layer to correct for the actual location of these fire pixels. And what you'll see in step 2 is the combined fire confidence from these two satellites. And in step 3, we applied a neighborhood smoothing around each pixel. And you can see sort of the values are more smooth now from 0 to 1. And in the fourth step, we applied a confidence threshold in order to mask out the low confidence values. And this threshold was defined and derived after we looked at the kind of final fire perimeter relative to MTBS perimeters that were derived from Landsat and Sentinel observations. So we ended up with a threshold of 0.95. And then from there, we can simply convert the raster to a vector. So unlike the FES algorithm, this is a image to vector-based algorithm. So you're starting with these pixels, and then you're transforming the pixels into a polygon. And you can do this every hour to get hourly perimeters for each fire. So what this looks like, I'll just go through this slide on technical details first, but essentially, as I said, we use both goes east and goes west. So we start with the active fire pixels. For this algorithm is not totally automated, so we actually have to make an input dictionary of sort of the temporal and spatial constraints. In order to kind of reduce the computational time and also fit the algorithm within the computational limits in Earth Engine. And we apply this terrain correction, which is necessary for the ghost data. And after that, we can derive the fire perimeter for each hour after ignition fire. And from the fire perimeter and active fire detections, we can also derive the active fire line and the fire spread rates for each fire as well. And what this looks like is something like this. This is for the 10 largest wildfires in California in 2020. And what you'll notice here is that each polygon here represents the fire perimeter at some interval after ignition, and the colors represent the timing of that perimeter after ignition. So the cooler colors are closer to ignition, and the warmer colors are closer to termination in the timing of that fire. And broadly, what we see is that this algorithm, which we call Gopher, it sacrifices some spatial resolution for a much increased temporal resolution. And we also compared our parameters to FEDS, which is based on VIIRS. What this looks like for the creek fire is on the left here, we have the Gopher parameters at hourly intervals. In the middle, we have the 12 hourly parameters from FEDS. And on the right here, we have the final parameters from Gopher and FEDS, but also the California CAL FIRE FRAP fire perimeters as well, which are very high resolution fire perimeters. And you can first notice that there's large gaps in the FEDS algorithm, where at 12 hourly intervals, particularly when the fire is spreading very rapidly, you get these really large gaps between fire perimeters. And Gopher, which is at hourly intervals, is able to fill in these gaps much better than FEDS. And it broadly sacrifices some spatial resolution as well. So you can see that in the detail of the polygons, where FEDS is much more detailed and more accurate in terms of the fire perimeter relative to GOES. But what's nice is that the final perimeters still between Gopher, FEDS, and FRAP, they match quite well relative to each other. And on the bottom here, I'm just showing the hourly growth in area from Gopher for the creek fire. And you'll notice that in the beginning, there was a lot of activity in the fire growth. And then later on, the fire became sort of quiescent. So broadly, Gopher can provide some insights into periods of extreme fire growth. And these are periods that we also really care about because they introduce very high stress on firefighting resources and cause a lot of destruction to nearby neighborhoods, and also injects a lot of smoke into the atmosphere and cause really bad air quality. And our kind of approach for mapping active fire lines, we developed two different approaches. So the first one we call concurrent active fire line length. And on the right, I'm just providing another pictorial depiction of this, of what this theoretically looks like. So we have first the fire perimeter at the first hour after ignition, and at ignition, this is just the centroid of the first fire perimeter. And then this kind of pentagon here is just showing the next fire perimeter in the hour after the first one. And so for this first sort of definition, what we basically do is to intersect the active fire detections with the perimeter in order to get this active fire line. So you can see this depiction of the gray fire perimeter outline, and then also the fire detections in red here. And then what you get at the end is this line that depicts the active fire line. And then for the other method, which we call retrospective, this one is defined as the intersection of the current fire perimeter and the difference of the future fire perimeter and the current fire perimeter. So for this definition, you actually need to know what the future fire perimeter looks like, but it's a more exact definition because we're kind of basically saying that the areas along the fire perimeter that leads to growth in the future perimeter is the active fire line. And then what this looks like for the creek fire is depicted in the charts on the left. The top is showing the concurrent active fire line length. And what's nice about Gopher is because we use that fire confidence in order to define the fire perimeters, we can also use the same approach to kind of delineate various confidence thresholds for the active fire line as well. So we're basically subsetting the active fire line more and more, and we can get to smaller subsections of the active fire line where we're most confident that that area might lead to growth in a future time step. So this will become more important when I talk about the modeling of the fire growth later on. And for the retrospective active fire line, this is depicted on the bottom here. This is generally more conservative in terms of the total active fire line length relative to the concurrent active fire line length. And generally, active fire lines and also fire spread rates provide additional insights on fire evolution and behavior. And I also created this visualization on Earth Engine apps of all of the Gopher kind of data. So this is just showing video of me going to the tool and exploring the data for the creek fire. And you can see similar sort of visualizations for the fire perimeters. And I also put in like charts for the active fire line length and the fire spread rates as well. And you can also go to individual time steps to see what the fire perimeter and also the various active fire lines look like as well. And aside from Gopher, it also has the feds data on here as well, and the fire perimeters, land cover, and also MTBS fire burn severity. And we also made some minor adjustments to the algorithm. So this is described on my GitHub repository if you're interested in how our current data set differs from the original one that we published in ESSD. Okay, so Gopher basically maps hourly fire characteristics, including the perimeter's active fire lines and fire spread rates. And for now, this is just for 28 large fires in California during this 3-year period. But we're hoping to expand this to 2024 and 2025, and also expand this algorithm to be more generalized across North and South America. And later on, we're also hoping to try to create another algorithm that fuses GOES and FEARS observations. So next, I'll talk a little bit about agency reports of suppression resources and personnel. And this is work done mostly by Andrea Delgado. So as you're probably really familiar with, the ICS 209 reports provide a lot of useful information about sort of the resources that are being put on various wildfires across the US. So including, for example, crews, dozers, engines, helicopters, and water tenders, and the number as these resources evolve throughout the lifetime of the wildfires. And so there's major barriers in trying to account for suppression effects in terms of wildfire modeling. For ICS 209 reports, first of all, there's a sparsity of reports compared to our satellite data. Generally, for major incidents, you have maybe 2 reports per day. There's a lot of human errors in these reports, including missing data or incorrect data entries. There's some duplicate incident numbers that causes various reports to be named the same, or there might be 2 different reports for the same fire. And there's also some errors where there's some data that are written within the text description, but not inputted into the tables as numbers. So another major barrier that we encountered was sort of how do we merge reports to account for complex fires or fires that merge later on during the lifetime of those fires. So for example, for the August complex fire, there were multiple reports for that fire. So we needed to create sort of ways to merge all of these reports together. And finally, how do we actually link these reports to the spatial data that we generated from either GOES or VIIRS? But despite all of these data quality issues, the ICS 209 reports, as you know, contain really rich information about these resources and also the impacts of these fires too, including various structure damages and evacuation numbers. And what I mean by some of these errors, and this is an example for the North Complex fire, and this time series here is just showing the total acreage of that fire with time, and the x-axis is the day of year for that particular year. And you can see that there's really large anomaly at the beginning or the first report within that series of reports for this fire. And this acreage is actually higher than the final area of that fire. So one of the things we needed to do is to correct for these kind of inaccuracies or anomalies in this data. And also that the acreage sometimes decreases as well. So we needed to account for that as well. Another error that we found, this is mostly if you wanted to look at the kind of structures that were destroyed or damaged from these fires. And what's really odd about the North Complex is if you just plot the data as is, you get this kind of sawtooth pattern, which doesn't make sense because this data should be the cumulative number of structures destroyed for this fire. And you'll also notice that the timing of when the structures were destroyed doesn't match when the fire was most active. And what happened here was that if you look more closely at these reports, you'll notice that they were saying that they put the right information within the text description, but because of some issues with the system, all of the numbers within the tables were zero during some reports. And so these technical issues led to basically inaccuracies in the data. And if we were to extract the numbers from the text, we actually get a much more realistic kind of time series of the structures destroyed. So if we look back to the acreage of the fire, now it matches quite well with the timing of when structures were destroyed. So next I'll talk a little bit about how we actually are using these data for modeling applications. And so first we needed to construct data tables and data cubes for modeling, and this is work supported by NSF grant. So we came up with several broad categories of data sets that we would need or drivers of fires. So first we have fire characteristics, so either from Gopher or FEDS, including the growth in fire area, active fire line, fire intensity, and ignitions. And we also came up with categories for drivers of fires, including meteorology. So, for example, vapor pressure deficit or wind speed, also land cover and fuels, topography, suppression, and sort of human environment factors like distance to nearest roads or infrastructure and housing density. And these are data from a variety of sources, including from the Land Fire Project or from ERA5, or this can be from a bunch of other data sets as well. And so again, what this looks like is, so first we had the ICS 209 reports, talked a little bit about the challenges of using these reports, that there's a sparsity of data, human errors, and some challenges with merging complex fires, which we sort of solved by first interpolating the data to hourly resolution. And then we were able to kind of sum up variables where it was necessary or take the maximum for a certain hour or something like that. So again, I know that there's been a lot of work done by the Earth Lab on ICS 209, but we found that we require some additional information from the raw reports relative to these previous efforts. And next, we linked the ICS 209 data to FRAP and also to FEDS and Gopher. So first, we looked at the longitude latitude coordinates of these fires relative to FRAP. But of course, sometimes the coordinates are actually outside of the final fire perimeter. So we needed to look at the incident numbers for various fires and sort of do some manual corrections in order to have them be better matched with each other. And from FRAP and the final fire perimeters, we're able to easily match that to the feds and the Gopher data. And so this is a much more detailed look at our process. So first we downloaded all of the reports, and then we processed the reports accounting for various errors in the report or inaccuracies. Then we interpolated various variables to hourly resolution. Then we merged reports for complex fires, for example, summing up values when necessary. And then finally, we filtered reports to the ones that we wanted to look at, particularly the wildfires or wildfire complexes. And then how the kind of crosswalk works is we first identified FRAP IDs and incident numbers that match with the ICS 209 data. Then we corrected for some IDs manually. And then finally, we merged FRAP perimeters where necessary as well. And for FRAP, this is necessary because for some of these earlier fire complexes, they actually had different IDs for different kind of fire perimeters within a complex. Like sometimes the fire perimeters, even though they're part of a complex, they're not actually merged together at the end into like a singular fire perimeter. And then with feds, this is some additional detail, which is that for feds, because the algorithm that we used at first was automated, this created some additional kind of thresholds that we needed to apply in order to crosswalk from ICS 209 to FRAP. And this is just looking at the final acreage for individual fires for FRAP and FETS. And you'll notice that most of the fires are along this one-to-one line, but there are some cases where the FETS algorithm, maybe because of a lack of detection for that fire, that the final acreage doesn't match very well with FRAP. And we then looked at sort of the time series of various variables using ICS 209 and FETS. So for example, this is showing in 2020 the time series of total personnel as well as the active fire line length and growth in area. And we also noticed that there were kind of differences in how these variables evolve with time. In particular, the growth in fire area evolves pretty rapidly with time, whereas the total personnel evolves pretty slowly, and there's also a lag between when the fire is kind of exploding in terms of the fire area and when the personnel can be deployed to that fire to respond to the changes in fire area. And so next I'll talk about some of the modeling work that we've done so far. So first, I've looked at some XGBoost or random forest models to try to predict the next hour or next 12-hour period of fire growth, for example. So this is, again, another pictorial depiction. And this is depicting the predictors that we use in this model, including the active fire line, the fire intensity, variance in elevation, as well as meteorological variables, including VPD and wind speed. We wanted to first just use a couple variables, like a pretty simple model, to try to see whether this would work for our designed problem. And I basically split up the data into a training and test set. And for feds, we have a longer period, whereas for Gopher, for now, we only have 3 years of data. So for Gopher, we're projecting the next hour's fire growth, and for feds, we're projecting the next 12 hours of fire growth. And this is just to show what the active fire line looks like for an example. This is for the creek fire about 37 to 38 hours after ignition. And the colors here represent the active fire line or different active fire lines in terms of the thresholds we applied using the fire confidence. So we're subsetting the fire line more and more with higher confidence. So you'll notice that the orange color here represents the highest confidence for this version of Gopher. And then the lower confidence is usually higher in terms of the total active fire line length. And the active fire line matters a lot because it sort of spatially constrains to where the fire can grow in the next time step. And it's a good indicator to where sort of along the fire perimeter, the fire is really hot and can grow or is likely to grow. And this is just showing some results that preliminary results that I've gotten for the Gopher and the FEDS model. On the top here, we have the Gopher, the observed versus predicted values. We generally get about 46% of variance explained for the training data set. And then for the test data set, which is 2021 fires, we get a 37% variance explained so far. And in general, the projected values are lower than the observed values. And from this random forest or XGBoost model, we can also get the importance of various predictors in our model. And we do find that the active fire line length has been the most important variable by far, but also including variables like FRP, which is the fire intensity, as well as meteorology can help improve the model as well. And this is an example prediction for the Dixie Fire in 2021. So the time series on the top here shows in black the observed sort of the satellite-derived fire-wide area, and the red here represents the predicted values from our model. And then on the bottom here, this is showing feds the 12 hourly prediction. And you'll notice that for a periods of extreme growth, that the model for now is unable to capture those kind of points there. And again, this is showing the maps of the fire progression for Gopher and feds. And you'll again notice that there's gaps in the fire progression because feds is at 12 hourly intervals. And we also wanted to explore the concept of how suppression influences fire growth during low versus high fire years. And our hypothesis is that during low fire years, that resources can be deployed to prevent wildfires much more effectively than high fire years. As you can imagine, if you have many fires that are occurring at the same time, those resources are going to be stretched thin. And so you're not as able to kind of contain all of those fires at the same time. So on interannual timescales, what we noticed is that we have this relationship where during high fire years, the total personnel days versus area here, you have this relationship where the kind of total personnel days relative to area kind of tapers off in these high fire years. And the colors here are just kind of arbitrarily grouping these years into low fire years and high fire years here. So this relationship here kind of implies some limitations in terms of resources being deployed to fires during low versus high fire years. And this is showing the time series of various years. On the top here, we have the growth in area as well as total personnel for various fires in high fire years, and then also for low fire years. And what you'll notice here is that the growth in area versus from high fire years and low fire years is pretty dramatic in terms of the daily growth in area. And then the total personnel is actually pretty similar between low fire years and high fire years, which suggests that the level of suppression resources being used doesn't vary as much or is not too dramatically different compared to the growth in area. And we're still trying to explore these data a bit more currently. And we also looked in more detail for two big fires, the August Complex in 2020 and the Dixie Fire in 2021. So, for example, in these reports, we are trying to see in the text-based data whether suppression resources were being diverted to other incidents, and also whether the growth of co-occurring fires affects resource availability on these major fires. This is a lot of detail, but on the top here, I'm showing the area, the cumulative acreage of the Dixie Fire in red here versus the total of all other co-occurring fires in the Northern California GAC. So all of these blue fires that are occurring within the zone. And you'll notice that there are various fires that kind of started within the lifetime of the Dixie Fire. And within the Dixie Fire reports, we are looking for whether there are instances of limited resources or resource availability kind of comments in these reports. And what we found is that in one comment, for example, that they say that emerging fires in the region are drawing scarce resources to new priorities. So this is sort of additional evidence that there are indeed limitations to resources being deployed to these fires in high fire years. Okay. And so finally, I'll briefly go over sort of smoke and public health in the US. And what recent studies have found is a reversal or slowdown in progress in reducing the amount of particulate matter and air quality. So again, for the Western US in particular, you have this reversal in the air pollution in these regions. And so just quickly, this is work led by Karina Chung, who's a current undergrad at Harvard. And we developed this framework to derive the smoke risk metric, which is a per grid cell contribution to regional smoke burden. And the kind of aim of this project is to optimize public health benefits for the entire region to reduce the most amount of smoke and to also look at whether we can target land management strategies in particular regions to reduce the most amount of smoke burden. So if you want to learn more about this project, we have a preprint currently online on Earth Archive. And we also created this app on Google Earth Engine, which you can go in and sort of explore various like land management strategies and how those strategies may help to reduce the overall smoke burden. And kind of the impetus for this project was that in the beginning, Makoto Kelp, who was a co-advisor on this project for Karina, and was looking a lot at prescribed burning. So for this project, we wanted to kind of research more about how pre-fire land management can help to reduce kind of the smoke burden on a regional timescale, and how the impacts of wildfire extends way beyond the immediate perimeter of those wildfires. Okay, so just to wrap up quickly, so I talked about some data advances and challenges, in particular focusing on the remote sensing of fire progression, fire tracking, using geostationary satellite data to map hourly fire progression, and also leveraging agency reports of suppression resources and personnel to supplement the spatial data, and then looking a little about how we can use that data to do modeling applications, and then finally looking a bit more at pre-fire land management in addition to kind of during fire management and suppression. But I'm happy to take any questions, and thank you all for your attention.
Questions? No? Really? No. Oh, well, I've got one. Thank you so much, Tina. This is Jennifer Baldwin, and it's so nice to hear about your work. Super cool. Are you familiar with our fired product for the MODIS clustering of burned area pixels? Just wondering if there's a way to your algorithm for VIIRS and for GOES is super cool. Do you think there's a way to integrate kind of our product or approach with yours to try and create a longer historical record?
Yeah, that's a great question. So, I haven't looked at your data set, which I believe is called Fired.
Yeah.
I have seen that you integrated that with the ICS 209 Plus, and it would be really great to try to integrate MODIS observations with VIIRS and GOES. One of the challenges that we've been having is sort of the kind of spatial offsets between GOES and VIIRS, which is that GOES is just much coarser in terms of spatial resolution compared to VIIRS. But we're currently really interested in trying like different approaches to either maybe use the time series of GOES active fire growth to kind of interpolate between VIIRS fire perimeters, but we can definitely try to use MODIS as well to extend even further back in time. But currently, we're actually trying to do the VIIRS algorithm retrospectively or retroactively to all of the MTBS perimeters as well. So we're creating a extended data set. For now, this is just for VIIRS, but using MODIS would also be great too. But I'm happy to chat further if you have any ideas of combining all of these data sets together.
Yeah, it'd be great to figure out what the collaboration potential is. And Lee St. Dennis, who's in the room too, also probably has some thoughts about the ICS 209 plus data, like if there's ways to take your lessons learned, and we're always working on that data set. So if you want to speak to that too, that'd be awesome.
Thank you. And thank you, Tina, for a great presentation. Yeah, I'm excited to see how you're using this. I also wanted to let you know that we're working on an update to the 209 Plus data set that will run through 2023, 2024. That's really a step forward. We've done a lot of work, particularly 2014 forward, to clean and duplicate the data. We're adding a whole layer on complex reporting to give much more daily information on complexes and summarized data, and also a much more robust resource usage record that's going to be folded in. And also we're folding the IMSR data on national and regional preparedness into the data set as well. And I'd be happy to talk with you further to see if there are particular elements that could be cleaned to support your work. more effective.
Yeah, that would be really amazing. And it's also like really great to see this resource that you put out with the ICS 209 Plus. And I'm really happy to hear that you're currently working on even more improvements to the data. And definitely fires in 2024 would be really interesting to look at, like for the park fire, and would be super interested in chatting further about that too.
Sure.
Oh, I've got one other quick question for you. What do you think the minimum fire size is for
Mhm.
GOES? Like, given that the algorithm or the data resolution is at between 2 and 3 kilometers, like, what do you think the smallest fire is that you could reasonably use your algorithm on?
Yeah, that's a great question. So far, I haven't explored too much on the minimum size threshold for different fires, but I suspect that it needs to be pretty large for the algorithm to be meaningful. Probably at least a couple thousand acres or 10,000 acres. And it probably also needs to be pretty long lasting as well, maybe at least like a day or so, to have enough observations to track the size of the fire. And another challenge that we had as well with using GOES is on the kind of diurnal cycle side, that kind of during the sunset period, Ghost East actually has lower number of active fire detections than we expect, probably from the angle at which the satellite is detecting the fires, or sun glint, or the just the viewing angle. So we found that actually using just the GOES West observations was better in terms of modeling the fire growth. But yeah, using the data is quite challenging. But there are some other efforts to combine. I also wanted to mention that they're using VIIRS and GOES to try to map out the fire emissions at much higher temporal frequency. I believe the data set is called RAVE.
Thank you.
Yeah.
Yeah, hi, this is Max Cook. I'm a PhD student with Jennifer here in the lab. Thanks for your presentation, it's really interesting. I'm working on a project that's using some VIIRS fire radiative power to look at sort of fire heat in the context of like environmental drivers. And I've been curious about the integration of FRP between GOES and VIIRS, and I wonder if you
Hmm.
have seen any potential issues there in terms of like how those retrievals are done or calculated. I saw that you were relating FRP cumulatively to fire size, which I think is really cool. And yeah, just wondering if you can speak to the differences between the two sensors and how to harmonize those FRP retrievals.
Yeah, so as I mentioned for the RAVE data set, they are using FRP, and they did do some adjustments between those two data sets, between VIIRS and GOES, to try to harmonize between the FRP observations. And I believe they have like different saturation of FRP in those data sets. So it can be pretty challenging to combine the FRP directly as well. Um, and yeah, I think in terms of the VIIRS FRP, the challenging part is because it's at these 12-hour intervals, you don't get actual FRP observations kind of between those like over past times. So you have to try to interpolate between over past times using GOES or some other assumptions. But definitely, I think the RAVE papers can help with kind of maybe initial steps to try to harmonize between those two data sets. But great question.
Thanks, Tina. We're about at time, but I did want to point you, there was a question in the chat
Yes.
about what types of urban land use promote or mitigate fire growth. Can this type of model be used to explore these scenarios?
Okay, let's see. Yeah, so currently we're not looking Very specifically at particular land uses, we're mostly looking at land management overall in terms of use of prescribed fires. Um, but yeah, we're currently trying to also look at field treatments in addition to prescribed fires to try to see whether these land management strategies actually help to prevent fire spread or mitigate fire severity. But currently it's pretty challenging. But yeah, definitely, I think in the future, if we have more empirical data or kind of models to try to relate different land management to fire progression or fire growth outcomes, then this can definitely be integrated into models as well.
Awesome. Thanks, Tina. That was wonderful. Really appreciate you coming. And give another round of applause.
Yeah, thanks so much, and thanks for all of the wonderful questions as well.
Thank you.
Thank you,
Thanks, Tina.
Tina.